first talk is from Tyler Conrad, who will be presenting on building the networks that build AI. Tyler is a tech lead at Arista Networks and has traveled from Austin to join us today. This is Tyler's first time presenting at NANOG. Welcome, Tyler.
All right. Thanks, everybody. All right, I didn't get any training on the clicker. I'm presuming it's just forward back. Yeah, there we go. Okay, one thing I do want to say in advance, my name is Tyler Conrad. I work for Arista. My title is now Principal Engineer. I'm not really sure what that means as of this morning, so that's a little out of date. But overall, just about me, been with the company for about 8 years, and I focus, well, I actually don't really focus on much of anything. My wife says I have ADHD or something. I like campus, I like data center, I like Wi-Fi, and AI is the latest hyper-focus. So that's about me. So the talk for today is really just all going to be about network infrastructure. So I don't want to talk to you about the latest AI agent or anything that can help you build networks. It's really about building the networks that build AI specifically. And there's mainly two types of networks that we're building for these days. There's training networks, which is where predominantly most of the infrastructure money has been spent so far. Those are going to be the big companies that are building their own models. Frankly, that's out of reach for most companies. If you're building a network for training, chances are you've got billions of dollars of CapEx available to you. However, inferencing, meaning you're using an already trained model, maybe running your inputs through it, getting an output. Like if you go to ChatGPT as an example, and you type something in, you're doing an inferencing query. And so that is relatively less expensive to run because it can run on a single GPU. But that being said, dynamics are changing a little bit in the market where we're starting to see a lot more inferencing and inferencing taking a lot more high bandwidth storage. And so we're going to start seeing some more spend towards inference that traditionally we haven't up to this point. So talking really about networking, what you see here is probably what most of you have worked on at some point in your career. Data center environment, maybe you've got layer 3 leaf spine. At this point, that's pretty common, but even if it's not, layer 2 leaf spine, core, dist, ag, whatever you have, the general point of it is you have services that you're delivering. So you have features that you require in the network, whether that's LACP down to the servers run by MLAG, Arista, VPC, ESI, whatever vendor you have that supports that. Some QoS, but maybe just throwing more 100 gig links at it is a better solution. But in general, you're running a lot of services that really need, well, flexibility and TCAM, frankly. When we switch over to AI centers, the main thing that changes is what we call the legacy data center, if you will, just gets renamed to front end. So your front end network is basically your existing data center. It might have higher bandwidth. So maybe you need 100 gig, 200, 400, potentially even 800 down to the host. But by and large, you're still using those same feature sets. You might be using LACP, you might be doing all routed ports and just doing all routed infrastructure. Great for you if you are. But in general, you need more TCAM, you need more flexibility in the front end. Another part of the network, so that's going to be really the CPU-driven part, is probably a good way to explain that. Now, the GPUs themselves are going to have their own network as well. So they sit on what we call the back end. Now, that's had a whole bunch of different names over time. There's a few more names out there now, like scale out is the popular one of the day. But you can use those kind of interchangeably, back end, scale out networking. And so the GPUs are going to need a lot of bandwidth between themselves. So if you have a 400 gig generation GPU as an example, it will use all 400 gigabit that you throw at it, like bar none. Now you need the ability to talk from any GPU to any GPU in that fabric losslessly and at high bandwidths. You don't really need much else. So on the back end, services don't really give you a lot of value. You need radix and you need speed. And so for that, you'll typically end up deploying a switch that can just basically get you as wide of a radix as possible. So what do the servers look like? On the left-hand side, you'll see an example of a fixed server something that has usually 8 GPUs inside of it. It'll have a couple CPUs, maybe a couple management or front-end NICs, and then a 1-to-1 ratio for backend, where every backend GPU has a backend NIC. On the right-hand side, you'll see what you'll see is mostly the rack scale architectures. So these are becoming more common lately. Usually they go to a more equivalent to like a line card host-based system, to where you have a compute tray, and on that tray is everything the tray needs to function. Meaning it has a CPU complex, management port, 4 GPUs usually, and then a dedicated NIC for each one of those. Now again, I'm really hyper-generalizing here just to try to make it more agnostic, but for the most part, that's kind of how these operate. So topologies. What ends up really defining your topology is how many GPUs you intend to connect to each other within the fabric. If you have a small cluster, maybe you're only connecting a handful of GPUs together, 8, well, you just need one chassis. You don't even need a network. If you have more than that, well, then you start adding switches involved. So if you have up to 1,000 GPUs, most vendors are going to have some kind of capability to do a modular leaf switch for you, where they can do, in our case, 576 ports of 800 gig. So you can divide that by 2 or multiply that by 2 to account for about 1,000 GPUs on a single device. Once you get beyond that, that's when you really need a leaf-spine network or a network fabric to be able to connect everything together. And so you'll see the scaling breakpoints down there. About 8,000 for fixed switches. Hybrid, which is a combination of maybe fixed leaves and modular spines, gets you about 73K. And then it just kind of goes bananas past that point with all modular. And then same thing for the next over. So the middle is what we call a 2-tier architecture, where you have 1 tier of leaves and 1 tier of spines. The right-hand side is what we consider a 3-tier architecture, where you have a tier of leaves, a tier of spines, and then you also have fabric plane. And that fabric plane is what gets you your radix. You need that scale to be able to scale larger, so to speak. And that's when it can really scale well, even in all fixed. So 524,000 roughly for a fixed, all fixed switch. Okay, I think oh, there it goes. All right. Let me make sure it didn't jump ahead. Yep. All right, so you'll see various topologies built in here. You might hear the term rails or planes, and we'll kind of touch on what those are. A rail isolated example is pretty much the most basic topology you can build, in that you have a leaf that all the GPUs connect to, and the host itself is separated by node IDs on those GPUs. So if a host has 8 GPUs as an example, it'll have node ID 0 through 7 assigned for each one of those GPUs. And it's almost like a rack rail system, where node 0 always connects to one leaf switch in the topology. And that's for all the nodes in that topology. Node 1 connects to the same leaf switch. And you'll see we've got 8 there, so we have 8 rails, so to speak. Well, if you need very low scale and you want to do fixed switches, that can work pretty well. But one of the caveats of it is if you ever need to cross that rail boundary, there's no way to do that except through the chassis itself. So inside these chassis, there's a capability in the collectives called PXN that allows you to use the scale up fabric. So similar to scale up is inside the chassis itself. It's what allows the nodes or the GPUs on the node to talk between each other, as well as maybe use each other's NICs. So you can go inside the host, hop onto a different rail, and then go out that way. So downside of this is maybe you don't have enough PXN bandwidth. Maybe something's broken on the chassis. Well, you don't have a backup path at that point. So you really have no way to connect other than through PXN. So once you get past rail isolated, you'll end up where you really have to consider subscription ratios. So most of these networks are built for at least 1-to-1 provisioning. And that's for a couple reasons. One is we pretty much define lossless as a requirement for these networks. Usually that's accomplished with features. PFC, ECN are common ones for that, which we'll touch on in a little bit. But if you have a full blast elephant flow, and you've got all the GPUs doing that, well, at some point, things are going to fall over. So that's why we build for at least 1-to-1. Some people are building even higher than that, like 1.25 to 1, to make it so that if you ever have link failures or anything negative happen in the network, you still have capacity. So you don't slow down the overall job completion time because of that. So next up, we have rail optimized. This is what I'm seeing most of my customers deploy. And the reason for that is mainly scalability and future state. So rail isolated has some real advantages. The main advantage it has is you don't need to use all the links on the uplink side of those switches, meaning every port can be a downlink. So you can get a wider fan out on the switch itself. Well, because of that downside of potentially needing more bandwidth for PXN and wanting more flexibility, a lot of customers are going this route, which means they use half the ports at least going up to a spine layer, and then the other half go down to the GPUs. So that cuts your scaling factor by about half for each of these devices. So that's why I say rail isolated does have a big advantage, but at this point, I'm not seeing a lot of people using it. With next gen, that may change. But the main thing that changes here is you'll still have the same number of rails. That'll be 4 for the rack scale architectures or 8 for the fixed architectures. And then those connect up to a leaf spine layer, and then that allows the collective to communicate over the leaf spine. But you still have some flexibility if you have a better latency factor to go PXN inside the node itself. You can use that to talk to the other rail and maybe skip the spine layer. Maybe the spine adds more latency. Maybe you want to go through this internal scale up fabric and you have lower latency to do that. It gives you the options. So it gives you flexibility. And then another one that you'll see is called non-rail or fat tree. I've seen it called a bunch of different things, but the gist of it is instead of connecting in a rail-based topology where the nodes connect up to an individual leaf switch and those are all different for each GPU on the node, well, you just connect everything up to the local leaf switch. So in this case, you've got a few hosts down there, and they're all connected to a top of rack leaf, if you will. So advantage to this is that you have the ability to use DACs or AECs. With rail optimized or rail isolated, generally you don't have the power footprint to do that. Meaning you can't get enough servers within a rack or even within adjacent racks to use all 8 rails or even all 4 rails simultaneously well. You're going to have some wasted bandwidth if you do that. With this, you can connect everything up and use cables that have, frankly, a lot better MTBF conditions. So one of the big issues we have in these deployments are really going to be the optics. I have a slide on this later, but basically to put it into perspective, you've got an optic that has about a 2.4 million hour MTBF. And in a 100K cluster, you'll have about 500,000 of these roughly, which means on average, about every 4.5 hours, an optic is going to fail in your environment. Well, unless you have a dedicated staff to go in and troubleshoot these, remove them from service, which that has its own caveats, and then put them back into service, you're always going to be chasing that dragon of how do we get our network back to 100%. That's a really big reason why people do over-provisioning. So because of that, non-rail gives you flexibility. So you can use the DACs or AECs, they are basically copper cables. So unless you bend them too much, they generally don't break that often. So much higher MTBFs, you can connect locally and be done with it. Now, disadvantage is you don't get the latency benefits of PXN. Meaning, even if you use PXN, every single GPU is connected to the same switch. So there's no real benefit to doing so. You might as well just send everything up to the leaf switch and have it come back down. If you want that latency benefit, you kind of have to use rails. So that way you have each individual GPU on a different switch. And then it's pretty common that for initial deployments, first getting started, that you don't necessarily need to build out the entire topology. Maybe you have a lab environment, you don't need to build all 8 switches or all 8 leaf switches. You only want to build out with 4 or 2 or 1. Totally viable. You basically just scope the number of ports for how many GPUs you plan to connect. It's building blocks. So if you need more ports, you add more leaves. If you need more bandwidth between those leaves, you add more spines. Now you can double up, triple up on links to the spines. There are some caveats with that, which we'll touch on. And I would be remiss if I didn't talk at least a little bit about IPv6 today, because I know that's kind of the topic of the decade. So 5549, 8950, as some people like to beat over my head with about, old habits die hard. is a really, really useful technology in these fabrics. So most of the GPUs themselves, they connect on IPv4. There's an exception with SRv6, but predominantly you're going to see v4 addressing used on the GPU itself. Well, whenever it connects up to the leaf, that'll be v4. But between leaf and spine, this is basically all greenfield networking. You can do whatever you want. And so you could go with a pure v6 underlay and then have link local advertisements, so 5549, and then transport those v4 addresses over the top of v6. Now, this gets you a couple really, really useful benefits. I don't know how many of you have local hands that connect the cable right every single time. In my experience, they connect it wrong almost every single time. And so 5549 gives you benefits in that we no longer have to put the IP addressing on the port itself. If you connect to the spine, if you at least get in the ballpark of where I wanted you to connect it, BGP is coming up. We're going to have a fabric going. Now, at some point for documentation and posterity, you want to move things back to where they should be. But this gives you the flexibility because, frankly, you spent a lot of money on these clusters. You probably want to get up as soon as possible to get some ROI out of it. So you can get up and running and then deal with the technical debt later. That's what we always say. And just a quick example, effectively, this is what a switch port config looks like, at least on Arista. So between leaf and spine, it's no switch port and IPv6 enable. That's it. Then on the BGP side, you just enable the address family on the interface itself. So neighbor interface, define the interfaces that want to do it, and then give it a peer group. So really simple to operate. All right, so something relatively new are going to be multiplane networks. So there's some big disadvantages to the way we've done AI networking up to this point. The most notable one is we're connecting one-to-one. Every GPU has a single link going out to the leaf. And well, that's not really very redundant. And the reason we do it that way is because we don't have enough bandwidth to be able to handle the lag technologies. We want the widest radix. We don't want those features, we want radix. So to move the goalposts, we can introduce multiplane that solves some of these problems. So NIC level redundancy, upstream congestion, upstream link failures. Instead of having one 400 gig, maybe we have two 200 gig fabrics. These don't have to connect to each other in the slightest. They can be completely separate. And what most people are doing is they're connecting an 800 gig optic in these individual GPU NICs, if you will. And they're splitting in a 2x400 gig mode. So where one 400 gig goes out to fabric A, one goes out to fabric B. Plane A, plane B is probably more appropriate. And what that does for you is you can make like a banana and split, where normally you'd have a single plane, 64 by 800 gig switch, you can have 32 spines, 64 leaves. Your scale isn't very high. It's about 2048 total, and that's your max radix in a 2-tier. If you split out, now you can run at a lower speed. So instead of running 1 by 800, you're running 2 by 400, connecting to two completely independent fabrics. They don't talk to each other, they don't need to. And by the way, all of this is on the NIC. The NIC itself has the intelligence to determine which fabric do we use and when. So in this case, we can quadruple our scale. So we can go from 2048 to 8192. And it gets progressively more impressive the wider you scale this out. To where now we can go, if you go to a 200 gig topology, so you split out 4 ways, which requires a crazy cable that we'll see in a second, you can get 32K in a single cluster. So all 2-tier, fixed, layer 3 leaf spine. And that's kind of the driver behind this, in that between leaf and spine, there's going to be some wasted bandwidth because you can't connect all the leaves. You have to use some uplinks, right? Well, between spine and super spine, it's 100% wasted bandwidth because all you're doing is adding subscription between all those leaf spine pods and doubling the number of optics that you need in your environment. So if you can keep it in a 2-tier, you can minimize the overall cost reduction, or actually maximize the cost reduction, as well as minimize the amount of bandwidth that you need between the fabrics. So let's talk optics. Generally, what you're going to see is on most modern switches, you're going to see 800 gig optics. And the current gen of GPUs are all 400 gig GPUs, really. They'll be using either 1 or 2 400 gig ports to connect to each other. And so if you break out that, you can have effectively a 64 spine, 128 leaf, and that's going to be your max density. That's 16,000 optics. It's a lot, even just 8,000 GPUs. That adds up in power. So we're talking not a lot in the grand scheme of things, because frankly, your overall network bandwidth and power, your network power is about 5% of your total deployment. So in a 100K cluster, you're looking at maybe 100 megawatt, and about 5 megawatt of that will be network. But we can't get more power. Power is very hard to come by. We're going around the country building data centers where the power is, because power and cooling are the two hardest things to get. So because of that, you'll see various vendors producing switches that have different cost-effective mechanisms on the optic side. So CPO is popular right now. LPO is one that we're putting out for the 800 gig generation. LRO is going to be similar to LPO. But generally, LPO itself, what's shipping today, is going to be moving the DSP to the switch chip. So effectively, the ASIC on the switch has a DSP in it, meaning we can skip that layer on the optic. Some of you may not realize optics themselves, they'll have a DSP on board to do the signal processing. That DSP adds roughly 100 nanoseconds worth of latency. It also adds a significant amount of heat. So on LPO optics, you cut that by about half, meaning if it's an 800 gig optic, your normal baseline is 16 watts. It cuts it down to about 8. So a pretty decent savings. And then not just power, but heat goes hand in hand with that. So that cuts that down too, and overall just makes the network run a little bit healthier. LPO will also run cooler because it doesn't have the DSP on. So we talked a little bit about optics and MTBF. If you can run your optics about 10 delta temperature cooler than what they are currently, which is what we're seeing with LPO. They'll run 10 degrees Celsius cooler. The general rule of thumb, and don't quote me on this, I'm not an electrical engineer, but there's a rule of thumb that says for every 10 C that the heat is increased, the MTBF halves. So just by nature, you should be running roughly double the MTBF. All right, now the good stuff. So load balancing and congestion control are probably the two biggest part of these networks that we're designing for. Layer 3 leaf spine, ECMP is king, where we have X number of spines, and each one of those spines should be connected to all the leaves in a 2-tier, or potentially a fabric tier that gets you connected to all the leaves and all the spines that way. But the idea here is you're going to stripe that bandwidth across all the spines that you have. Now, a thing that people like to try to do is summarization, because they see a lot of routes in the fabric and they don't like that. So they want to summarize and have maybe a default route coming down from the spines or something along those lines. You can do summarization, but you have to really do it on the leaf layer. Maybe you use /31s for all the GPUs that connect up and aggregate that to a /25 or something along those lines at the leaf, and then you can do summarization, because there's no black hole effect there, where if the leaf goes away, well, those devices are dead anyway, so it doesn't really matter. But if you do summarization at the spine layer, now you have a problem, where maybe a spine gets disconnected from a leaf. It has no way to signal that to you without when you summarize. And so there's going to be a few load balancing options we'll see. The top two, ECMP hashing, like your general ECMP, typically has not worked well in these deployments for AI. And most of that comes from, in the very beginning, RDMA was port 4791 as a source, port 4791 as a dest, and the only real entropy was gathered by the source IP, dest IP. Maybe if your ASIC supported it, source port, like physical port, dest port, source MAC, dest MAC. So not really a whole lot of entropy to be gathered there. Because of that, a lot of vendors implemented RDMA-aware ECMP hashing, where we look further into the payload to look to see what the individual queue pairs are. So these are going to be the transactional identifiers that are used whenever you're having the collective communicate, so that way we know for tracking what flows what. And we can use that as an integer to use for additional entropy. Frankly, we don't really need that anymore. Most of the collectives, so RICL and NICL at least, starting about last summer, started supporting the ability to dynamically derive the source port based on the queue pair ID anyway. So kind of moot. Next up, we have cluster load balancing. So this is an Arista-specific feature where what we do is we look at topology, define the collective based on the flows we receive, and then build a forwarding topology based off that. So we can have collective members in collective A talk via a certain path, and collective B talking in a different path. It's static pinning with more steps, effectively, and it does work pretty well. The next one that we're seeing, or really hearing a lot more about than seeing, is SRv6 traffic steering. So this is pretty cool. It gives you the ability to run IPv6 the host itself. So the NIC is really going to have an IPv4 and IPv6 tunnel. The GPU is still going to have a v4 address, effectively. It's going to be wrapped in an IPv6 IP and IP packet, and then used as SRv6 for source routing to determine which hops through the network should we traverse. Now, this requires a controller. So it's going to be out of reach for most enterprises, frankly, because the controller itself needs a lot of network visibility. What paths are in use, what paths are going to be in use. There needs to be some schedule interaction whenever you spin up the jobs, so that way it knows which paths to statically pin, because that's what it's doing. It's statically pinning paths for you. I haven't seen an open source implementation of this, so it's probably a ways out for general purpose, but it is what it is. Now, if you have the ability to support packet spraying, which is a NIC feature, there's a few more avenues open to you. We no longer have to care as much about individual hashing, meaning the flows arrive and then something happens at the NIC layer to split them. So maybe the NIC alters the source port, maybe it alters a queue pair ID, maybe it creates a virtual queue pair. It does something to create individual flows from that, and then that allows them to hash differently. So they'll all arrive at the same leaf switch, but they'll have different entropy values that force them to go different paths through the network. So very useful. AMD and NVIDIA both support this. Could be useful for you and your networks. But if you are using hashing, so regular hashing, it's going to be elephant flows effectively. There's ways to break it up by using a larger number of queue pairs. Queue pair number kind of makes the number of flows that you have. So instead of a single 400 gig, maybe you'll start out with 8 by 50 if you have 8 queue pairs. But at the end of the day, it's still hashing. So a good behavior is traffic arrives at the leaf and it picks 2 different uplinks to go for 2 different flows. A bad behavior to have is traffic arrives at the leaf and it goes to the same spine, because these are 400 gig flows and now somebody's going to pay the toll. Enter dynamic load balancing. Most vendors have something looking vaguely like this, where traffic arrives, it looks at a table internally, determines which path is unused at the moment, and then forwards out via said path. So it allows you to react to flows that arrive and have a little bit more perfect distribution. And I say a little bit, it's actually a lot of bit more perfect distribution. Now, there's a lot of acronyms on here. Basically, there's DCQCN, which is Data Center Quantized Congestion Notification, mouthful, which for network operators, we really care about the next word, which is RockE v2. And really, we care about the next 2 words, which is PFC and ECN. That's what matters to us. So those other 2, they're implemented at the NIC level itself. PFC, ECN are what we connect and integrate with on the network. So PFC is hop by hop, where each individual packet that arrives, it'll go via, let's say, GPU1 to the backend leaf to AI spine. And each one of those hops has its own congestion control mechanism. So it uses a specific queue value to determine, what ingress queue am I looking at and what egress queue am I looking at. And then as flows fill up, your ingress queue flows your egress queue. And eventually, if you have bad hashing, at some point you're going to have a setup where 400 gig flows collide and now are trying to take up more bandwidth than the port has capable. So at that point, you're going to have queue back pressure. So the egress queue starts to fill up, and now the ingress queue starts to fill up. That's when PFC kicks in, priority flow control. So what will happen here is we've got on the top 2 levels of leaf spine, a couple flows that are coming through. They're going to the same leaf. they'll have a PFC pause come in whenever congestion is experienced and the queue fills to whatever threshold you have configured. And it will pause and notify the upstream device because it experienced traffic from said ingress queue that you need to stop sending to me. That can actually flow end to end through the network to the point where it gets to the sending GPU if you let it, which isn't a great situation to be in because there's a concept called a victim flow. If you look here, we've got the top flow that's going to that third leaf on the right-hand side is actually not really talking to a congested endpoint. It's talking to GPU 5, which, yeah, GPU 5 on the bottom right-hand side. So it's not really even in the path of congestion. It just happened to get unlucky and hit a leaf switch that had an ingress queue that was filling up. And because of that, it got a PFC pause. And so one of the ways of mitigating this, going back a couple slides, is ECN. So ECN is end-to-end congestion control, where the GPU, as it sends RDMA traffic from end to end, will have a special bit in it. And that bit, let's see, sorry, bouncing around a minute, will have basically the IP ECN flag on it. So this is called ECT, ECN capable traffic. This has to be configured and marked appropriately. If your GPUs are not set up appropriately, meaning the NICs aren't set up appropriately to do DCQCN with ECN enabled, what's going to happen is anytime we have a packet that was supposed to be marked for ECN, we're going to drop it. And that's part of the IETF spec. But ECN, what it'll do is it rides over the existing RDMA flow. So you've got GPU to leaf to the other GPU. That's the flow overall topology. Well, when congestion is experienced on the leaf, it goes ahead and marks the ECN bits and say, we experience congestion. And that bit propagates through to the endpoint. Now, the endpoint sees this bit being marked, and it's responsible for sending what's called a CNP, a congestion notification packet, back to the original sender. So that's the extent of what the network does. The network just says, we saw congestion. The end hosts do something else. So in most cases, they overreact. They're going to drop their bandwidth by about 50% and lower your overall job completion time. So this needs to be tuned on the GPU nodes. But this gives you the capability of no longer allowing that back pressure and those victim flows to take effect. Because effectively, PFC is your overall backstop. It allows you to have a true lossless network. That is what makes the network lossless. But we need some way to tell the sender to back off, to stop sending so fast without PFC going end to end. Because the second it does that, the entire network is full of victim flows. And that's where ECN comes in. Now, ECN is probabilistic, which means you'll have some kind of configuration on the switch. In this case, it's a min of 256 kilobytes and a max of 512 kilobytes. What that really means is the queue size. So as the queue size hits 256, we're going to start marking progressively. We won't start doing it on every single packet. We'll make it between whatever our max mark threshold was. In this case, it's 20%. So our probability of marking is linear between 0 and 20%. And it goes up as you go up in buffer utilization. So as you hit 512, it's now 20%. The second you hit 513, it's now 100%. Every single packet gets marked. And so this is a quickie little diagram kind of explaining that with ECN and PFC combined, you can potentially mitigate the victim flow scenario because ECN doesn't usually kick in fast enough to stop the tier 0 to tier 1 PFC, but it will react fast enough to stop the tier 1 to T2 in most cases. All right, quality of service. So basically in AI networks, there's going to be only a few queues that are really leveraged. Your strict priority queues are going to be 6, 7, and then maybe 4. These are going to be, the 6, 7 are a mix of network control traffic like BGP and everything else you expect. But for the data traffic that we're carrying across us, it's going to be the CNP packets. Those should be your top priority because the sooner those get to the source, the sooner your network slows down and you don't trigger congestion control anymore. 4 is your RDMA control. So when Nickel and Rickle set up jobs, they communicate the queue pairs over this packet, and you want that to be as quick as possible. Beyond that, we switch to weighted round robin. So your first queue there is going to usually be Q3. That's going to be your RDMA bulk data. So this should only be RDMA flows. This will be your lossless queue. So you turn that on to prevent loss in this specific queue. And then you'll have a scavenger queue of 0, 1, whatever you want to do below that. And usually there's going to be some kind of bandwidth allocation there, like 95, 99% to the waitless or lossless queue, and then everything else just flows to 1. All right, segmentation. So when we build these networks, you have a couple choices. If you're building for a single tenant, segmentation is less relevant. But if you're building for any kind of multi-tenancy, maybe you have some other customers, maybe you have a shared environment in some way, segmentation is very critical. One of the ways of doing that is with VLANs. So keep in mind, we're using all routed links. So we can't exactly trunk between leaf and spine because then you're in powers of 2. You can't really do too much about that. But if we have some kind of encapsulation over the top, we can run across those routed links and use those effectively. In this case, EVPN with VXLAN. So we can have a VLAN stretched across the fabric to allow the GPUs to talk to each other. The downside of that is what's visualized here, where what happens whenever we have a MAC or an ARP miss in an L2 fabric? We have a flood condition. And with 400 gig flows, you have a really bad day. There's some tunables to help mitigate this by effectively making it so instead of a miss doing a flood, you can have a miss do a drop. But overall, we recommend just don't even design for this if you can. Another mechanism is using VRFs. So if you have a virtual routing forwarding instance, you have an isolated routing table for an individual tenant. Now, VRFs are locally significant generally. So if you program them on the leaf, you'd either have to run a ton of sub-interfaces up to the spine and then do the VRF Fiesta all the way across the fabric, which I've done and I don't recommend, or you run an encapsulation over the top. So again, back to VXLAN EVPN because we really like it. We can run a bunch of VRFs across there and have segmentation for individual customers while still maintaining the VRF end-to-end across the fabric. And then we have the SRv6 approach. So with SRv6, we have a concept of microSID. This is encoded as effectively source routing into the payload. So I mentioned earlier, it's an IPv6 payload with an IPv4 packet embedded inside of it effectively. What's going to happen is you're going to encode the individual hops that you want to hop through in that v6 address for the destination IP. And so that'll have the SID of each path along the way you want to hit. So you could program it to go to leaf 1 to spine 1 to leaf 5 directly. Or you could do something nonsensical, leaf 1 to spine 1 to leaf 3 to spine 2 back to spine 5. It's up to you and really up to your controller to program this and tell it what to do. If you want, there is a handy container lab topology, so if you want to play with this, I have it on my GitHub. Feel free to download it, run container lab. You'll need a VEOS or CEOS license, or not license, sorry, CEOS container image for that. But beyond that, I mean, you're off to the races. All right, and coming up pretty close to time, common problems in these networks. The most common problem is going to be QoS mismatch. So the GPUs, NICs, they all have to be programmed exactly end to end. And they don't usually come built the way you want directly from the factory. So you have to go in and tell it what you want for each hop along the way. Every node has to be programmed and all 8 NICs on the node have to be programmed. So there's a lot of touch points where things can go wrong. This could be on the host. It could even be on the network. Maybe you didn't configure QoS on the network the way you thought you did. So looking for drop counters in a lossless queue is usually a good idea. Looking around, just trying to determine, is everything forwarding the way we expect it to? The second most common is incorrect cabling. So like I mentioned earlier, an 8K cluster is variably between 16,000 and 20,000 optics. That is a lot of patch cables. And when you're building these things in the order of days, it's not a great time to be trying to figure out where things are. So 1, run LLDP. It'll help you out a lot. 2, hope you have a really good cabling contractor. The next one is going to be dirty fiber and optics. So this should be no surprise to everybody here. Connectors get dust in them. People breathe on them thinking it gets rid of the dust and adds more dust. It causes problems. And these MPO12, MPO16 connectors are very sensitive to dust. So what we'll often see in the field is somebody maybe will move a cable around, get dust in there, and now you have to RMA an optic because they can't necessarily clean it very well. It's a big issue. And then past that point, it's day-to-day things. So like your initial NICs bring-ups, you'll need to make sure the speed, the FEC, and the auto-nag are all matching. That can be a problem depending on vendors. Some vendors have an idea that it should be one way. Another vendor may think it should be another by default. And so you'll have to come up with some way to make the two match. MMU tuning, meaning on the network silicon, tuning the individual queues, how much bandwidth they get, the memory manager itself, like if you have PFC headroom caps, overall the alpha values, which are used to determine how soon we kick in PFC. Thing about congestion control is the sooner it kicks in, the more bandwidth you lose. So you want it to kick in as late as possible without dropping traffic. And that's what tuning's for. Congestion control tuning, kind of the same thing there. And then one that's particularly painful are these soft hard failures. If you end up building a topology, it's very difficult, you as an operator, to tell if everything is working the way it's intended to without doing benchmarking. And when you do benchmarking, it doesn't exactly tell you where the fault is. So you could have a soft failure in your memory module, it could be at the NIC, it could be something in the fabric. But what's going to happen is the same thing that always happens. The network's the problem. We have slow job completion time because of the network. So you need data to be able to show why the network is forwarding the way it's supposed to. Meaning, are we dropping traffic? What's our flow data look like? Do we have any telemetry? Things like that. And then this is what I mentioned about optics. For a 100K build, you've got about 515,000 optics and about 4.5 failures a day, or 4.5 hours between failures, so 5 failures a day. It's a lot, and I really don't like it. I really don't like optics. All right, and then key takeaways. The front end is probably what you're used to. More speed, maybe higher subscription ratios, but generally features are still in the know. Back end or scale out, you're probably building a brand new network for this. Chances are, if you have a network, it doesn't have enough bandwidth, it wasn't built for 1-to-1 or greater subscription ratios, and most people are refreshing these about every 18 months, because every 18 months we double bandwidth. And it just so happens every 18 months a new GPU comes out that can use that bandwidth. So it's constant chasing your tail. Power and heat, that is the problem to solve. So like I mentioned, we're building these clusters all around the US. I am seeing most of these in the US, but they are expanding around the world. So other places are getting clusters. It seems like most of the spend does seem to be in the US today, at least from what I've seen. But really, we're still limited by power and heat. So we're going to where it is. Where can we cool it? If it's naturally cool, great. If we have water there, that's another problem. Power. And then overall, just careful monitoring the network. You need to make sure that you have telemetry to tell what's wrong, when it happened. SNMP polling is probably not going to be super useful for you, especially with those soft failure conditions where things may flap and come back and look good, and then you have to hope that you had SNMP traps turned on to be able to tell, oh, it actually did go down and come back, or something along those lines. All right, and with that, I guess let's open up Q&A.
Thank you, Tyler. Good job, especially for your first talk here.
Yeah, thanks. Appreciate that.
Yeah, if we have any questions, yeah, looks like over there.
Hi.
Please state your name and affiliation, by the way, after you're done being blinded. Apologies.
That's fantastic. Hi, everyone. Good afternoon. My name is Sudhi. I'm with Meta. I wanted to go back to the topologies you were showing before. You had the rail optimized and followed by the fat tree topology. The uplink capacity would be identical if I understood the nuance between the two. Could you talk a little bit more about when you would use fat tree versus rail optimized, and what are the pros and cons, if any?
Yeah, of course. So you're exactly right. The subscription ratios don't really change there. Now, they could potentially change with rail optimized, meaning you don't necessarily need to use the leaf spines every single time. So there's some flexibility if you know your workloads very well and they work well with PXN and you can account for how much total bandwidth they're going to need. Maybe we can oversubscribe between leaf and spine or between spine and super spine. You really have to know the data, though, to go in to make that decision. So what most people are doing is they're planning for one-to-one to begin with because they don't know right now. We're still, for a lot of customers, still in the experimentation phase, trying to figure out what their model is going to look like, what collectives are going to look like. But again, I mentioned the fat tree piece, like rail optimized versus fat tree. Rail optimized, if you build for it, has a big advantage in latency. Fat tree, the main advantage is you can use top of racks again, so that's nice, but also you get the DAC capability. So you can use higher MTBF transceivers so that maybe you have a person running around a lot less in the data center fixing things. That make sense? Cool.
If you're attending remotely, please submit a question of the remote Q&A.
Hi, Ido Kadim from CPacket. Can you say more about what telemetry you do use to manage these networks appropriately, given what you said about having data?
So I mean, I'm a vendor. I have opinions. Cloud Vision is what we would typically pitch for a customer, but we're kind of agnostic in what you bring to the table. So if you wanted to use open telemetry like Telegraph, Grafana, one of the other open source alternatives, really the thing that matters is that you've got something built to collect that data. Visualization is going to be the most important thing for you. Does that make sense?
What kind of data would you look at?
So you want to look specifically at the main things that matter. How much bandwidth is each port sending? So like overall traffic graphing. You want to see how many drops you receive in specific queues. So you want to see if Q3 is your lossless queue. You want to know exactly if you drop any traffic in Q3 because that is your red herring, that something is majorly wrong. Red herring is a poor choice there. That is a true fact that something is probably wrong in your environment. Beyond that, looking for general QoS patterns, flow data in general, things like that are really useful to have, but less impactful than those first two.
Thank you.
Mm-hmm.
Hi, Tom Sullivan, Jane Street. In regards to the PXN operations, when we have analyzed nickel operations before, we have found things like send, receive, and whatnot would not consider all GPUs, and therefore would not see other paths as potential proxy operations, and therefore PXN wouldn't even be considered. Wondering if you've seen anything similar where, sure, all reduce has no problem with your rail only because it can use PXN for all the things, but were you seeing PXN fail in some other cases?
I mean, all-to-all is your worst case scenario. If you have all-to-all going, you're going to have a bad time with PXN on current generation GPUs from what I've seen. Now, again, I haven't seen the latest gen with all-to-all with rail isolated. Maybe that is perfectly fine. I don't have any customers that have built for that specifically, but I'm curious to know if you find any.
Thank you.
Well, thank you, Tyler.
All right.
Looking forward to your next contribution.
Appreciate it.
Well.